So we were talking about insulation, and today we are going to define the critical insulation radius. Okay, but before we go through that kind of equation, um, we need to first define or say that the main purpose of insulation is, of course, to impede heat transfer, right? That's why we add insulations to our homes, for example, or to our pipes. However, sometimes we have the wrong idea that we would expect that if we insulate a pipe, we would decrease, the heat transfer from the pipe to the surroundings. Like no matter what, we put insulation and it's going to happen. But it's not always true. Why? Because we have two competing heat transfer modes, and one of them is going to dominate over the other. So not all the time this is going to happen. And the explanation, I put it here in this slide so you don't forget it. The additional insulation increases the conduction heat transfer of the insulation layer, but decreases the convection resistance of the surface because of the increase in the outer surface area for convection. So we have a compromise, right? Convection and conduction are competing there, okay? So the heat transfer from the pipe may increase or decrease depending on which one dominates, okay? So we have a competition there. That's why we need to define a critical radius for the insulation to work. In the beginning that in every process, we will have competing the three modes of heat transfer, right? In this case, conduction and convection are competing for that. So to define or come up with the equation to calculate the critical insulation, thickness of an insulation, we are going to start with our equation for heat transfer for a cylindrical insulation layer. So imagine you have this insulation layer. How many resistances we will have for this layer? We will have two, right? The one conduction due to the insulation itself, right? And the one due to the boundary layer with the surroundings, the convective one, 1, 2. So the heat transfer rate for a cylindrical insulation layer is going to be delta T over the sum of the resistances. Two resistances, one conductive, again, because of the insulation layer itself, and one convective because it is surrounded by the environment, right? So we have a thermal boundary layer development there between the insulation solid and the surroundings, the fluid. So we are going to use this equation later on to solve a problem. So if we take this equation, this heat transfer expression for our insulation layer, and we differentiate with respect to R naught, right, the outer radius, and equal it to 0, we can get a very simple equation to calculate the critical insulation radius that I'm going to show in the next slide. So after differentiation, z equal to 0, we have the critical insulation radius is K over H, where RC is the critical insulation radius. So what we are doing to calculate the critical radius? We are essentially comparing how important is conduction to convection, right? It's a ratio. We are comparing the two modes of heat transfer that are competing to help us to determine that critical radius for insulation, right? On top, we have K, right? That is related to conduction, right? And in the denominator, we have H, the convective heat transfer coefficient that is related to convection. So we are comparing which one is more important, right? That's what we established in the previous slides. So critical radius, K over H. And we can have two different cases. We can have the case where the pipe outside radius is smaller than our calculated critical radius. In that case, the heat transfer would increase by adding insulation until the critical value is reached, we can have the case where the pipe outside radius is bigger than the critical radius. In that case, heat transfer is going to decrease as more insulation is added. Okay, so these more or less can help us to determine, okay, yes, by comparing the outside radius with our calculated critical radius, if really adding more insulation is going to benefit or not, right? We have these two main cases. Okay, so let's calculate the critical radius of insulation in this pipe. So we need to find first the critical insulation radius for cellular glass with a K value of 0.051 watt meter Kelvin when the heat transfer coefficient or the H is 3. Calculate the heat loss per meter length for a 3/8-inch Schedule 80 steel pipe. If the outside surface of the pipe is maintained at 350 and the temperature of the surrounding air is 30, perform the heat loss calculation for the bare pipe and for the pipe insulated with the critical radius of cellular glass insulation. So we have the nominal size. You need to check in Appendix 2 in your textbook for the outside diameter for that nominal size. So this will help you again to look into your appendixes and learn how to find these values in your text. So this is my calculation here. And so 2 pi, the radius for the 3/8-inch scheduled pipe is 0.00855 meters. In the appendix book, you read it in inches, being 0.675 inches. So per meter length, with the H value given, hot minus cold, I got 51.6 watts per meter. Again, with Newton's cooling law, because we are calculating the heat loss for the pipe, the bare pipe, right, is convection. So the third question then is how much is the heat loss for the insulated pipe with the critical radius of cellular glass insulation. That means for that calculation, we are going to use the critical radius. So in that case, how you plan to calculate the heat loss? If you, for the pipe insulated with the critical radius. And we define it here, right, in this slide. So we will have one resistance due to the insulation plus the one through the surroundings, because we have the formation of the boundary layer, right? So this is the equation we are going to use, but we are going to do calculations with the critical insulation, which means, right, that we are going to replace R naught in our formula by RC, by the critical radius. Why? Because the problem says that. How much is perform heat loss calculation for the pipe insulated with the critical radius of cellular glass insulation? So again, we will be using the formula that we established in our previous slide, slide 16, right? So to find the heat loss from the insulated pipe, we are going to consider the resistance of the insulation and the thermal boundary layer outside the insulation, right? The convective resistance. Then the heat loss per meter length of insulated pipe is going to be delta T over the sum of the resistances. One because of the insulation, the next one because of the formation of thermal boundary layer due to convection, right? But we want to find the heat loss for the critical radius insulation because that's what the problem requires. So we are going to replace R naught by RC, the RC value that we calculated first, that it was K over H, right? And then that will give us the heat loss from the insulated pipe. So if you see delta T is the same, right? This is the critical radius because it's R naught over Ri, but we are replacing R naught by RC, the critical value. We have the K value, and we have also the H value here given. So that gives us 60.8 watts per meter. So as you can see, by adding cellular glass insulation to this pipe, we increase the heat loss from 50.6 watts per meter to 60.8 watts per meter. So it was an increase of heat loss of 17.8. So it was beneficial or not to add the insulation.